San Jose has actually has become even more creative. They decided to use the tip as a pickup tool, so they can apply potential in different way to absorb, essentially pick up an atom from here, and then move to another location, and then deposit this atom. So it's like a little construction tool, if you like, construction tool. You can have a bunch of atoms here. You pick it up, move it, pick it up, move it. You construct a ring structure like this, right? So these are individual atoms that they construct. I believe is they do this on a copper surface, and they build up this little ring structure. And because they have a ring structure, each of the atom has electronic waves, and they interfere with each other and create little ring structure. It's called quantum coral structure. It's a very fascinating thing. It takes a very skilled STM user to build a little ring of atom like this. And you can do a lot of fascinating physics by looking at quantum coral and stuff like this. Okay, so that's our imaging technique. These are usually morphology, and then there are other tools, and I will go through quickly now, that there are other tools that allow you to look at structure, but not in an imaging way. They're physical structure. They're infrared spectroscopy, of course, IR. People are familiar with it from undergraduate. We all have looked at infrared spectroscopy. By looking at surface vibration, you can characterize the geometry and the length of your vibration. So this is a classic Baud-based technique, but it's ported to surface analysis. Something similar to refractive IR spectroscopy is something called electron energy loss spectroscopy, which uses slow-moving electron beam, typically under 10 electron volt, and then you look at the energy loss suffered by this primary electron beam. So it's kind of like vibrational spectroscopy without a photon. And this is a typical commercial spectrometer. Electron beam is created on one of little tiny electron source, and it go around this little hemisphere cylinder, so-called cylinder analyzer, and then your sample is positioned right in the middle here, and then there's a lens and then detector on here. And what you see is that you have a primary electron scattering elastic peak down here. That's of the order of 5 to 10 electron volt. And then you measure slower electron, because these are the electrons that suffer energy loss, that excited your material, excited a vibrational excitation on the surface. And you see a little peak like this. Exactly what you see with infrared spectroscopy. And each of these peaks correspond to different vibration, surface vibration or vibration of your absorbing. Okay, so that's so much for physical structure, because you can look at morphology, or you can look at using spectrometry. You can identify from their vibrational frequency the strength of each of the vibration, the arrangement of the partial vibration. You see, not a microscopy tool, but a spectroscopy tool. And then you would have electronic structure determination, which we'll talk about as the second part of the course. You have angle resolved photo emission for electron spectroscopy, whereby you look at Fermi energy level, surface state, band structure, and things like this. This looks foreign to you now, but we'll explain this later when we go into electronic structure determination. It's a very important tool. Nobel Prize, 2 Nobel Prizes have been given on this tool, including the one to Einstein, of course. So Einstein was awarded Nobel Prize 1921, I think, for explaining the photoelectric effect, and not because of relativity, but for photoemission effect. So we'll talk a little bit more about, in particular, how you use photoemission electron emission of a photoelectron to probe the electronic structure of your material that you see. There is a very nice course notes that I make a link to here, and they discuss principle of X-ray spectroscopy, X-ray electron spectroscopy. So let me just briefly talk about this quickly. This tells you a little bit what happens when the material absorbs an X-ray photons. When your photon is high enough, this is represented by the red line. What would happen? You can excite the material, and you could have excite a bound electron to an empty electron orbital up in the high up. So this corresponds to your absorption, X-ray absorption that you see. So it corresponds to XSAT, that little absorption edge that we got, right? And then once you got excited to this is not a very stable phenomenon. What will happen is that this high-line electron in this high-line orbital can come back when de-excited. So when it comes back, it will fluoresce a X-ray photon. This is called EDAX when we do electron microscopy, because you can excite the material not just by photons, but also fast moving electrons as well. Same phenomena occur. But here we are talking about our excitation particle is an X-ray photon, but it could be a high-energy electron. So you would have X-ray fluorescence spectroscopy, right? So this is the basic principle of X-ray fluorescence. But then of course, if this impinging electron can excite the electron to a bound electron orbital, empty bound electron orbital, or you could also eject it directly. So in this case, if you eject an electron out into the continuum, in other words, it's no longer hanging around your material, it's out there, right? This becomes a free electron. Then what you have photoelectron spectroscopy or photoemission spectroscopy. And if you have an X-ray source as your excitation particle, then you have X-ray photoelectron spectroscopy. If you use a ultraviolet photon, UV source, then you have a ultraviolet photoelectron spectroscopy, right? So that's what happened. So that's what gives rise to this XPS, so-called XPS phenomenon that you see. Okay, so this sort of summarizes what would happen to absorption of photon. You have absorption spectroscopy, basically absorption spectroscopy, or you have emission through electron spectroscopy by ejecting the electron outright like this. I don't want to go too deeply into the experimental part, but just to impress you that it is a complicated phenomenon because your photon can have a polarization vector. If you do your photoelectron with the linear polarized light at the synchrotron, then your polarization vector, in other words, what is a polarization vector? Well, if you look at photon, right? Photon, what is photon? Photon is electromagnetic wave, right? So usually you would have electric field, right? You would have electric field. So here what I'm trying to draw, electric field vector. So this is my magnetic field, usually is B vector, and they are orthogonal to each other. And this one is my electric field, usually it's called A vector. So and this is my photon direction. Okay, so this is EM wave, right, which is a photon, right? This is my photon. And so when you say linear polarized, it means that my A vector is along a certain axis, right? Not in any direction, right? As if non-linear polarized, like an X-ray lamp, that is non-linear polarized. That means that the A vector can be in any orientation along this axis. Whereas if you are in a synchrotron, your A vector is aligned in the direction of the synchrotron ring. And so you have to take into consideration of the polarization vector when you do this type of spectroscopy. And so it could become a little bit complicated. And this note describes